Alright, so it turns out mic was disconnected when I recorded. Um, Somehow happened. But anyway, this is going to be the FRQ review, part 2 for units 1 through 4 and 6. So I'm just going to provide commentary. So for the first one, it's going to be a definition question. It's mainly going to be just defining like the formula for it. I think that's the best way to do this problem. But yeah, so in this case, moment is going to be the force times the distance. More specifically, it's like the distance from the pivot multiplied by the force that is perpendicular to the bar or something that you're going off of. So yeah. So if we put this into like actual symbols, we get that the moment is actually equal to the force times the distance. Right? And you should know that each of these represent like the definition that you just wrote above. But yeah, so the second part is talking about the SI base units of the moment of a force. So we're just going to rewrite it. And then F times S. We know that S is just going to be distance, so it's going to be meters. And F is equal to MA, the product of MA. And then we can just substitute the SI units for those. And then after that, we can combine the like terms and the exponents. Hooray. But yeah. Okay, for the second problem, or the second part of it, we're going to be doing this like multi-part question. This diagram in the top right is mainly just giving information. Even though it says part B, it's mainly like going over a question that we haven't covered yet. But yeah. So we're given that the length of the rod is going to be 2.4 meters and has a weight of 5.2 meters. Which is shown. And then we're later going to see in part C that this weight and the distance actually comes into play. Let me just wait for me to stop yapping and move on to the actual question. So we see that there are actually like 3 forces on the rod. So there's a string attached to B, and there's also a support stick perpendicular to the rod at C, and then there's the weight at D. And there's a tension in the string that pulls the rod down. And additionally, the weight of the rod pulls the rod down at an angle. And we also know that the rod is in equilibrium. That means that the sum of the moments is going to be equal to 0. Yeah, because that's the definition of equilibrium. It's also like the resultant force is equal to 0 too. But in this case, we don't really have to calculate it because that's not what they're asking for right now. But anyway, for component Roman numeral I, we're going to show that the component of the weight is perpendicular to the rod is 4.3 newtons. So we can draw a diagram here to be a little bit more clear. So the rod is going to be the slanted, and the arrow, the vector going down, is going to be the weight, which has a magnitude of 5.2 newtons and is at an angle of 56 degrees. We know that the dotted line here I'm drawing is the perpendicular to the rod A. And since it's perpendicular, it has an angle of 90 when like at the intersection. So the angle that I'm drawing right now and erasing is going to be 34 degrees. And this 34 degrees is important because we can now calculate like the component of that is perpendicular to A. In this case, it's going to be adjacent to the angle, so we're going to use the cosine trig function. So it's going to be 5.2 newtons multiplied by cosine of 30. And here I'm just fumbling with my calculator. But it's going to be 4.3 newtons, which was to be shown in the problem. So for Roman numeral 2, by taking moments about end A of the rod, calculate the tension of T. So we know that the rod is going to be in equilibrium. So we have to make sure that the moments is equal to 0. And in order for the moments to be equal to 0, the sum of the anti-clockwise moments has to be equal to the sum of the clockwise moments, right? So using this information, we can actually start like creating an equation for the anti-clockwise moment, which I'm about to show quite soon. So the anti-clockwise moments, it's just going to be going like towards the water, right? So the forces that are going anti-clockwise in this case is going to be the string as well as the weight. The string in this case is going to be T. We're going to put it as a variable T because we don't know it. We're going to solve for it. Multiply the distance of the entire rod, which is going to be 2.4 meters. Added of the moment of the weight, which is going to be 1.2 meters multiplied by 4.3 newtons. And then we can simplify this into 5.16 plus 2.4 t. And since we calculate the anti-clockwise, we can now calculate the clockwise, which is just going to be away from the water, right? And the only force that satisfies this is the stick, which we can calculate the 4.6 newtons multiplied by the distance from A, which is just going to be 1.8 meters. And you can calculate this out. And you get 8.28. And we'll move it to a place where I have more space. And then you have a one variable equation that you can solve for. 5.16 plus 2.4 t is equal to 8.28. And you subtract this, you get 2.4 t is equal to 3.12, and then divide by 2.4, and then you should get t is equal to 1.3, I believe. Yep. Alright, so number 5, so it's another definition problem that is similar to the first problem that we did here, defining the moment. So you can cheese this question, just write the formula, but be a little bit more detailed. So the mass of an object multiplied by the acceleration of the object, basically. But yeah. And I think I'm just like re-explaining this, but this is just gonna be like the formula because F equals ma, right? But the thing about Cambridge is that their mark schemes, they'll allow you to just write the definition and words, which I did here. So now we're actually getting into the bulk of the question. So we have these two blocks that are colliding with each other, and they have different momentums before and after. And yeah, I'm just explaining the details here. So X is going right at 0.37, block Y is going left at 0.65, and then afterwards, after they collide, the X box is going to be moving left 0.13, and then Y is also going to be moving to the left. So if we get to the actual problem, come on, Brian, you got this. So kinetic energy in this case is going to be equal to 1/2 mv squared. Where kinetic energy is equal to 1/2 m, and then I pause here because it turns out in this problem they don't directly give you m here. So you have to improvise a little bit and then look at what they actually give you. In this case, they actually give you momentum. And you have to use the formula of momentum, right? So the formula of momentum is going to be P is equal to mv, where it's going to be mass times velocity. In this case, P is going to be 0.37 initially for block X, and that's going to be equal to mv. Right now we don't have to solve for like the products or individual ones, but we can use the equation the equation for kinetic energy. So it's going to be 0.3 is equal to 1/2 m times v, and since v is squared, it's just v times v, right? And then we just substitute our momentum thing, and then we solve for v. Calculate a moment, which is going to be equal to 1.6216, and then we resub it into our momentum equation, which is going to be mass times 1.62. And then it's one variable equation, which is divide m is equal to 0.228, and then to round it to 2 sig figs, it's going to be 0.23. Now for part B, determine the magnitude of the momentum of block Y after the collision. Since I have a short-term memory, I have a bad short-term memory, I have to redraw the diagram to make sure that I'm doing it correctly. So block X, blocks Y, they're moving before and after. So for B, determine the magnitude of the momentum of block Y after the collision. So in this case, we're going to use the conservation of momentum for inelastic and elastic collisions for these types of problems. The momentum is going to be the same before and after. So you can actually make an equation, equal, how do you say it? Like equaling both the before and after momentum. So in this case, the before is going to be 0.37 plus negative 0.65, because 0.65 is going the other direction. It's going left. Similarly, this negative 0.13 is going to the left, so it's going to be negative. I kind of botched that, but it's negative because it's going to the left. So we can solve this, and then we get that X is equal to 0.15 or negative 0.145, but they're looking for the magnitude of the momentum. So in this case, our answer is going to be positive. Struggling with definition problems. Can you believe it? Which means greater than or equal to 0. Now for C, block X exerts an average force of 7.7 newtons on block Y during the collision. Calculate the time that the blocks are in contact with each other. So through Newton's second law, force is going to be equal to the change in momentum or the change in time. If you don't know, the delta just means change in. So the delta P is going to be change in P. So we're going to substitute the values that we know, 7.7 newtons. And then our change in momentum is going to be mistake moment, negative 0.13 minus 0.37. The reason why we do it in this order is because in terms of change, you always want to subtract the final value first. So it's going to be final minus the initial always. And then we don't know t, so we're just going to put it as t, and then we're going to solve for t. And then you plug this value into the calculator. You simplify and plug it into the calculator, and then you get 0.065 seconds. Oh no, I think I got lost. Wait, no, I think I'm just re-explaining it, to be honest. Okay, never mind. For 6a, state Newton's first law of motion. So this is one of the first things you learn, and one of the things you should memorize, because Newton's laws actually come up a lot. But in this case, Newton's first law is just going to be an object stays at rest if it's already at rest, and an object in motion will stay in motion, basically. But these two conditions are only satisfied only if no resultant force acts on it. So I'm going to write here, an object at rest will stay at rest, or an object at motion will stay in motion. Misspelling error. In motion, unless a resultant force acts on it. But in this case, we're going to look at this question and through its description. But it turns out, for the majority of this question, except for the diagrams, it's kind of just blabbing, because the question that we're supposed to answer is actually focusing on Newton's third law, right? So it describes how forces exist in pairs, and one such pair of forces is the weight of the disk and another force y. So you want to state the direction of force y, as well as the name of the body on which force y acts on. So we know that the weight of an object, right, it goes down, and thus the equal and opposite reaction for that is going to be going upwards, right? So that's simply a definition problem. If you don't know, this is one of the easier marks, I should say, to get based on the definition, right? It goes upwards. And the second part that is of the question is a little bit harder to get, simply because it's a little bit unintuitive. But we're looking for the name of the body of which y acts on. Please draw a diagram. Please draw a good diagram. But basically, if we have our object, right, and it's going down, it turns out that weight is influenced by Earth, right? So weight is just going to be the force of Earth on the object, but the equal and opposite reaction is going to be on the other object, right? So in this case, it's going to be Earth on the object, right? And this is because based on the third law, it's going to be the same pairs of objects. You can't switch the pairs of objects and say that, oh, since the forces are going in opposite directions and they're equal, surely this is it, right? But no, it has to be the same object in order for the equal and opposite reaction to actually occur, right? So I'm drawing a diagram here of two objects. This is what gravity is, right? There's an additional force of like normal force, an example shown, but this is like the bare bones of what we're seeing in this problem. But yeah, so this is going to be the end of it. Thank you for sticking to the end. Be sure to like, subscribe.